Hi everyone, have you ever wondered how you get your talk approved at DroidCon? I think we've cracked the code. Welcome to another talk about Jetpack Compose. My name is Markus and I work at Sentry as an Android engineer.
And my name is Roman. I work together with Markus on the Android SDK at Sentry. At Sentry we build application monitoring in production, including exception handling, performance, profiling, whatsoever. And today we want to talk about auto instrumentation for Jetpack Compose specifically. But let's start with a... Yes. Can we make it louder, actually? Is it good? Better? Good. So let's start with a simple example. Imagine we have a Compose application. In this case, it's going to be now on Android, which probably many of you know because it's used as a showcase for showcasing latest Compose features. And this app has a crash. So if you are publishing your app in production, you're most likely using some monitoring tool. In our case, we're going to use Sentry. So if a crash happens, you upload this to Sentry. After that, you enter your dashboard or console or whatever, and you see the stack trace there. In this case, we think the crash is actually pretty simple. So we know the line number and we know the file name, which is the topic screen and the line 255. What you do next, you open your source code and you see on the line 255 there is actually nothing suspicious. So it's just a function call, nothing that should be breaking. And you are confused at this point. So you start investigating this by reproducing the steps that your user did. So you open the app first. After that, you switch the tabs to a different screen. You want to select a different topic on the list. And after that, you also want to follow this topic. So you click the follow button. And after that, the crash happens. This sequence of events we actually call breadcrumbs. And what is breadcrumbs, in essence, is a trail of events that happened prior to an exception. Usually it contains events like navigation, user interactions, HTTP requests, activity lifecycle events, and so on. And this is also useful as a metadata for your crashes, so you can actually see, for example, which list item was clicked prior to a crash. At Sentry, we also support breadcrumbs, so we have a special section on the issue details page. You can filter by different type of breadcrumbs. You can search for different breadcrumbs and so on. But for now, specifically, I want to focus on the navigation breadcrumbs. So you can see from which to which screen the user has navigated prior to the crash and what were the arguments for this navigation route. If we'll take a look back at now an Android example, they use an Android X navigation library, and there you would have to define a navigation host, which provides different routes. So if you want to add a breadcrumb, you would import a bunch of Sentry imports, and you would call sentry.add_breadcrumb and create a breadcrumb with a category of navigation, level info, and some metadata, like from which to which route the navigation event was performed. But we started to think that this is pretty tedious to do this because you have to do this for every navigation event in every place of your app where you want to track this. And before we jump into implementation details, a few words about our SDK design philosophy. So we want our users our SDK to be easy to get started. We want to provide great value out of the box with minimal configuration. And we also want to keep low SDK footprint in source code of the app, so you don't even notice that we actually instrument your app and collect telemetry. So the question is, how can we automate this for our users? For navigation, as I mentioned already, now an Android uses Android X Navigation Compose, and the usage looks roughly like this. So you would, as a step one, you would retrieve the navigation controller from this remember nav control method. Next step, you would actually define the navigation host, which is kind of like a router if you are familiar with React development, for example. And there you would define your routes and what screen your user has to go after that. And the the next step, if you want to navigate, you would just simply call navigation controller.navigate, and then you would provide the route. What is cool about this navigation compose library is just basically a wrapper around the regular Android X navigation. And if you look at the Java doc of this library, we will find a handy interface, which is called onDestinationChangeListener, which provides us a method onDestinationChanged, which is basically a callback whenever a user navigates from one screen to another. We will be notified in this callback. So let's just go ahead and implement this navigation listener. So we just start simply by creating a class called Sentry Navigation Listener, which implements this interface. As a next step, we would keep actually a previous destination, because the callback just gives us the current destination. And if you want to tell our customers or SDK users from which screen was actually the navigation event performed, we also have to keep it ourselves. And then we would just implement this method onDestinationChanged, which has a bunch of handy parameters like destination arguments. And inside that, we would already create a breadcrumb. So we'd call sentry.addBreadcrumb, create a breadcrumb with a type of navigation, and we would set some useful metadata, which then will be reflected on Sentry in the navigation, in the breadcrumbs section. Yeah, so we just provide here from which screen to which screen using the route field, and what were the arguments of this navigation event. At this point, we might think that we're actually done. So this was the usage example. And if we want to use our Sentry Navigation Listener, we would just simply call add onDestinationChangeListener. But there might be multiple problems with that. For example, if our customers or SDK users would call this multiple times, or if they forgot to remove this navigation listener, we would end up reporting multiple breadcrumbs for a single navigation event. So we started looking into ways how we can actually control that better. And our idea was to bind this to the activity lifecycle. So when our activity enters the onResume state, we would actually add the destination listener or navigation listener, and when it enters onPause state, we would remove it. And this way, we would ensure that there is only one navigation listener at when the screen is active. So to do that, we actually would use the Android X lifecycle library, which provides us with the lifecycle event observer, which is a simple interface with a single method on state changed, which is called whenever the lifecycle changes, or lifecycle of the activity changes. Yes, and we also provide the navigation controller here as a constructor parameter, because we want to use it later. So we would create an instance of the Sentry Navigation Listener from the previous steps, and we would implement this onStateChanged method, which basically gives us the event. So basically the lifecycle event of the activity. And if it's on resume state, we would add the navigation listener, and if it's on pause, we would remove it. As the last step in all this, to connect the dots basically, so we want to tie this with Compose. And how we want to do this, Compose provides this local lifecycle owner. For convenience, we just created this extension function, which we called with Sentry observable effect. And it has to be a composable function, because we would like to use it inside another composable function. And from this local lifecycle owner, we can retrieve the current lifecycle object. After that, we would create our observer, and we would actually add our observer to this lifecycle. But another thing, what we want to do is actually also remove the observer to not consume unnecessary resources when the composable leaves the composition, or whenever any of the lifecycle or nav controller instances change. So for that, there is a special side effect from Compose, which is called the disposable effect. And it provides us with the onDispose callback, which we actually can use to remove the observer and free up the resources. Yeah, and this is only triggered, I mean, not only, but yeah, it's triggered when lifecycle or navigation controller change, or when the composable leaves the composition. Remember where we started? So on the left side, you see how we would do this if you would implement this manually. And on the right side, you would see the new way with our extension function, so it's just a single function call, and then we already provide value out of the box, so we track all of your navigation events across your app, and you don't need to do this manually in every place. But why stop there? We actually do even more right now. So this is the usage without our Gradle plugin, and if you would use our Gradle plugin, we do some bytecode manipulation to actually automatically add this extension function to any navigation controller instance, so you don't have to worry about that at all. And in this case, you wouldn't even see any Sentry imports or any Sentry functions in there, but this is worth another huge talk because bytecode manipulation is a huge topic, and I gave a talk last year at DroidCon. You can watch it also.
Knowing the changes from one screen to another is nice, but we also want to give some more details on a specific screen, and that's why we built this user interaction breadcrumbs, which basically are any kind of clicks, scrolls, or swipe gestures within your app. In a very naive approach, let's assume we have a login screen with a login button, and every time the user clicks on the login button, we want to track those breadcrumbs. So how do we do that? We just call our SDK, right, and add the breadcrumb there. No, we don't want to do that because it would just really clutter the app code with unnecessary calls, and it also feels a bit of repetitive kind of, yeah, it's not very readable, and the best code is actually the code you don't have to write because you don't have to maintain it, and it cannot break. So let's get rid of this. So we had this idea of also automating the generation of user interaction breadcrumbs. And what we would need to do is to detect any clicks, swipes, or scroll gestures globally within your whole app. We also would need to know which widget you actually clicked on, and then create a breadcrumb automatically based on this. So how can you detect a click within your app globally? Fun enough, there is a callback existing since API level 1 you can use, and the callback in question is the window.callback. So you can set this callback, you retrieve the window via the activity, and then you have this dispatch touch event method you can use, and you can consume any motion event being forwarded to your window. So that's a good start. Then we can simply tie in a gesture detector to actually detect clicks. The same, of course, works for scrolls and swipes, but here I'm really just to keep it simple, focusing on clicks. So we feed in all the touch events to our gesture listener, and as a last step, we also override the onGesture listener, and now we have this nice on single tap up callback, and we get every click event, which is great. In order to make this work also for multi-activity apps, you would simply need to use the existing activity lifecycle callbacks. So you could hook into every activity, set your callback, and you can detect all those clicks. We quickly realized, although this was working just fine, overriding the window callback is not a good idea, at least not this way, because you override any existing callback. And the Android system actually is using this callback. For example, when you have a dialog and you click outside the dialog should be usually dismissed, and that's what the Android system is actually using in the background. So in order to not break any existing functionality, we also need to have or save the existing callback away. Here we call it default callback. And for every overridden method, we feed it back into the existing callback. So it's like really keeping the chain of callbacks intact, being a good API citizen, I would say, and making sure we don't break any existing functionality. So this is great. We now know when the user clicked, but we have no idea what the user clicked on. So we have to go deeper. So how can we identify widgets? Here's also where the path a bit diverges between the Android view system and Jetpack Compose, but more on that later. So in the classic Android view system, you can actually access the view hierarchy. So we start with the window.decor view. We have a list of candidates, and now we kind of traverse the view hierarchy, view after view. If the view is a view group, it means it has child views, so we add those views to the list, and we again can iterate over those items. Not every view is actually relevant as a click target, so we just have some additional logic. So we check if the motion event with the X and Y coordinates matches with the view we are looking at. Also, we check, for example, if the view is clickable or not. There are some more finer details, which I'm sparing you, but that's basically how it works. Now we know the user clicked, we know which view the user clicked on, but we still don't have a really good identifier because view is just like an object. We maybe can get the class definition, but we don't know a really good identifier. And calling view.getID just gives you an integer, which is also not very human readable. But luckily, again, the Android SDK to the rescue. There's a way to reverse look up the resource name of your widget. So we can call view.getResources, getResourceName. We supply the view ID, and voila, we are back at our login button. As mentioned earlier, we are not done yet. So this works nice for the Android view system, but it doesn't work for Jetpack Compose, because under the hood, Jetpack Compose is not using any Android system widgets. It's doing all the drawing logic on its own. So when we look at the view hierarchy, it somewhere stops at this Android Compose view, which takes care of all the rendering. So there's a lot of like details hidden from us and from the Android view system. So we need to dig deeper. Along our research, we stumbled upon accessibility, and we quickly saw that it actually tries to solve a similar problem. So when you click on a region on your screen, you want to have a textual representation. That sounded really very much like what we needed. And when digging deeper, we also saw that the underlying mechanism, which Jetpack Compose is using, is semantics. Here I have some source code of the icon composable you can find in the Android X libraries. And what it's doing, it's taking the content description and transforming it into this modifier.semantics call. And then this modifier is simply attached to your composable, and then at runtime, when accessibility is enabled, you can read out this information again. So it was nice to see how that works. It's also interesting that the semantics are not just used for accessibility, but you can also use it, for example, for UI testing. So maybe some of you have seen this modifier.test tag. Under the hood, it's just calling modifier.semantics. So you set this test tag, and when you execute your UI test, you can reference back based on this tag and then perform, for example, a scroll gesture or a click. Yeah, digging deeper, we also found out that accessibility is nice, but it's not really a good fit for our use case. There's this very nice Android Compose view accessibility delegate compat.android.kt you can look into. It has a few thousand lines of code. But it really was not a good use case for us because the content for accessibility is localized. For crash reporting, that's not really ideal because you would end up with one crash per language, and usually you don't want to have your error monitoring tool cluttered with duplicate crashes. You just want to solve one issue, right? Another downside is that Jetpack Compose accessibility is actually disabled by default. So unless you enable it in the Android view system, Android system, it won't be populated. So all the information which we would need is not presented in the APIs we could access. But since we already dug a bit deeper, we also saw the semantics are still there. So why not access them directly? And before we can do that, we also have to understand a bit how Jetpack Compose works under the hood in the terms of semantics and composition. So we have our composable code. During runtime, your composable code is executed. That's the process of the composition. And in the end, we get a UI node tree, which sounds very similar to the view hierarchy, and it is very similar. And the good thing is that those semantics you supply in your composable code are always transferred up to your UI node tree. So even at runtime, you can access those. This UI node tree on Android exists of two different types of nodes. There are those layout nodes, for example, for text, but there are also vector drawables nodes, which are called V nodes under the hood. This Android Compose view we saw earlier in this Android system view hierarchy also implements an owner interface, which we now can use to access the root of the Jetpack Compose UI node view hierarchy. And now the task is quite similar, so we just want to iterate through this tree, read out the semantics, and find a matching node. Here's some code. It's actually quite similar to what we saw for the Android view system, so we still can check if a node is part of the view system, like node.isPlaced. We can also check if the coordinates of the node match with our touch target, and this way we can simply identify if the node and the click and the motion event all fit together. Having implemented that, we still saw a few downsides. So some of those APIs are marked as internal using the Kotlin internal keyword. And as it turns out, you cannot use internal functionality within another module. You will get a compile time error in Kotlin. It also turns out if you access those Kotlin APIs using Java, you turn your Kotlin compile time error into a Java compile time warning, which is good enough for us and solves the use case. But it still requires everyone to add those test tags, and it's not always feasible to do that. So we actually went further down the rabbit hole and now looked into Kotlin compiler plugins to solve the last missing piece of our puzzle. If anyone from JetBrains is in this room, please bear with me. This is just a mental model. It's not 100% correct. So when we compile Kotlin code, we start off with our source code. It gets parsed. We have a tree representation of the source code. Then comes the IR builder, which creates an intermediate representation of our source code. This one runs through the backend, and depending which backend you're using, you end up with platform-specific code. In case of Android, it's the JVM bytecode. To better understand how Kotlin compiler plugins works, we have to understand this IR tree better. So this is created by the builder, and then inside the backend, all the plugins are being executed, and they allow you to modify this IR tree. Here I have a very basic example of how this IR tree can look like. So on the top we have some very basic Kotlin source code, an example function. It takes an argument and just prints out a line. On the bottom we see this IR tree, and it's already kind of enriched with a lot of information. For example, the name argument is already resolved, and we see a correct type definition of Kotlin.string. Also, what we call Kotlin synthetic sugar, all the nice features we have, they get desugared at some point. So in this case, your string template is being transformed into this string concatenation element within your IR tree. There are a few more things. For example, also the comment doesn't exist anymore because it's not relevant for compilation. Any if statement you would write would have been transformed to a when statement. So there's a lot of stuff going on inside the Kotlin compiler. Now when we look at the very basic composable, in this case an empty one, we compile it, and then we check back what the Jetpack Compose compiler plugin is doing, we quickly realize it's doing a lot. And I just want to highlight a few features to better understand some of the background. For example, for every composable function you define, the compiler plugin will automatically add a composer and a changed argument to your composable. This is also the reason why, compared to Flutter, your composables never need to return any kind of widget, because this composer gets kind of injected into your code and can keep track of all the UI elements you are creating. There's also this changed parameter, which is more or less a bitmap, which allows Compose to better understand which parts of your composable changed and be more efficient when recomposition is happening. Another nice thing is the source information, which only gets added when enabled. So when you are using Android Studio, you are working on your composable, you have the preview open, you click on the preview, and it links you back to the source code. That's the source information working in the background for you. There's a lot of more stuff happening, even for an empty composable, but that's also probably too much for this talk. So we kind of move on, and now we have our Sentry Kotlin compiler plugin, which is also enriching composables in a way that it takes the name of your composable and automatically adds modifiers to your source code. So in this way you don't have to do it on your own. It also does some more, like there are more complex examples when the modifier is already present, then they need to be changed, of course. But in this case, that's basically what our Kotlin compiler plugin does. Dialing back to the login screen example, we can now see just by applying our Kotlin compiler plugin, we don't need to clutter any of our code with specific, like add this and that breadcrumb. It just happens automatically, makes it easier to read and easier to manage. So whenever you just write a new composable, you just don't need to think about tracking. It just works out of the box, and you will see your breadcrumbs in our backend. But that's not all. Like having done all those steps through the Android system and the Kotlin internals, we realized that we can do better. So we already have a few plans on enriching the modifier.clickable to make it even more actionable and give you more context information.
Yeah, then we also, is it turned on? Sorry? No, it's not.
No, it is.
It is? Yeah, good. So we're also looking into adding this special sentry trace annotation, which you can add to your composable functions, and then we would automatically measure the time it took to render this composable and to compose itself.
We are also looking into automating and providing you with the composable performance metrics and tying them together into your build, so you also get more detailed information on what changed over release and where potential performance impact is happening.
Yeah, and here you can see some references of our work. So compiler plugin and the Gradle plugin, they are in the same repo. Sentry-ended SDK and some references that we use across this presentation as now an Android app and Android X sources. And everything is open source at Sentry. You can go check it out. And if you use Sentry, open GitHub issues. Let us know if something doesn't work. And with that, we'd like to thank you for coming here. And we still have time for questions, I guess.